Okay, so today I'm going to be talking about the problem of trisecting the angle. Now, we kind of know how to trisect a 90-degree angle, but we're talking about a general case here. If we were to try and trisect any given angle that we can get, can we do it with a compass and ruler? Now this goes back into the ancient Greeks, where the Greek mathematician called Euclid, he published a book called Euclid's Elements, in which he gave a way to bisect an angle just using a compass and a ruler. So we already know that is constructible, and so since you can bisect an angle, you can just keep repeating that sort of algorithm to bisect an angle again. You know, divide an angle by 4, even if you want to divide an angle by 8, 16. You can do that because Euclid's Elements can give a way to do that. So the next general question that people had is, okay, if we can divide an angle by 2 or divide an angle by 4, what about if we just try and divide an angle by 3? So the first mathematician that we had record of trying to solve this problem is the Greek mathematician Hippias. And since then, we had other Greek mathematicians. Archimedes has tried his hand on it. There's Diomedes, and so lots of people have tried. And then came around the 1800s, Carl Friedrich Gauss, who is known for, if you know in linear algebra, Gaussian elimination or the Gaussian curve in statistics. He stated that it's pretty much impossible to trisect the general angle or double the cube, which will come in at a later time in this video. But he did not leave any proof, and it was up to a guy named Dunham in 1837. He published the proof in a paper called "The Research on the Means of Knowing if a Problem of Geometry Can Be Solved with a Compass and a Straight Edge." So, until that point, we had no idea, but now we have a proof that says that it's actually impossible. Alright, so I'm going to lead you into the proof with a couple of facts. First, if the angle theta is constructible, then we can also construct a segment of length cosine of theta. And you can see from this drawing that we can pretty much give a line segment of length 1 with really any 2 points. But from there, if theta can be constructed, then that means a length of cosine of theta can be constructed just by seeing this. We're also going to be covering a lot of different trig identities. Sine squared theta plus cosine squared theta is equal to 1. This is of course like a big trig identity you need to know. You can take the sine of the addition of two angles. You can take a cosine of the addition of 2 angles, and that would mean that you can find what the sine of 2 theta is, which is 2 sine theta cosine of theta, and you can find what cosine of 2 theta is, which is cosine squared theta minus sine squared theta, and then you can also check that this is equal to 2 cosine squared theta minus 1. Alright, and then we get to the big theorem, which is if a segment of length alpha is constructible and alpha is not in the rationals already, then the degree of q adjoint alpha with respect to q, that's going to be equal to 2 to the power of r for some non-integer r. Alright, so we're going to begin our proof by contradiction by supposing that we can trisect any constructible angle. Now first we need to actually get a constructible angle. So I'm going to try and use 60 degrees. Now how do we know that that's constructible? Well, we can just use this. Now we can just use this simple proof. Take any 2 points, draw the line segment out with a ruler, and take your compass and make a circle around with the radius as the line segment. So we have 2 endpoints right here. I'm drawing the circle with the center on one endpoint, and then the radius, and then the radius of the circle is defined by the other line segment, and then we can also do that to the other endpoint. So what you will find is that we're going to have 2 points of intersection. It doesn't matter which one you choose, you just have to choose one of them. Right? Now take your ruler and connect that intersection with the 2 endpoints that you made. Right? So this will give, I claim that this will give an equilateral triangle. Right? These two edges right here, they are of the same length because they are in the radius of this circle, and these two sides are of the same length because they are of the radius of this circle. So all 3 sides have the same length. They are an equilateral triangle, and further on, we note that the equilateral triangles have angles 60 degrees. Like all the angles of the equilateral triangle are 60 degrees. So the angle 60 degrees is constructible. Okay, so let theta be the angle such that 3 theta is equal to 60 degrees. So pretty much, let's trisect the angle. And we noted from our assumption that this theta has to be constructible. And that means, from our fact above, this fact right here, that the line segment with length cosine of theta, I'm just going to call that length alpha, that is also constructible. Now, cosine of 3 theta is just cosine of 60 degrees, which is 1/2. We know that part already. Then, we can use our trig identities to find that cosine of 3 theta, which is equal to cosine of 2 theta plus theta, which is equal to cosine of 2 theta cosine theta minus sine 2 theta sine theta. With just a bit of algebra, we can show that this is equal to 4 cosine cubed theta minus 3 cosine of theta. And since we defined a line segment of length alpha to be length cosine of theta to be alpha, that means that cosine of 3 theta is equal to 4 alpha cubed minus 3 alpha, in which that's also equal to 1/2. So alpha satisfies the equation that 1/2 is equal to 4 alpha cubed minus 3 alpha, which, you know, a little bit more algebra is needed, but you can also show that alpha satisfies that 8 alpha cubed minus 6 alpha minus 1 is equal to 0. Alright, so we're going to take the polynomial 8x cubed minus 6x minus 1, we'll call this f. We're going to take this polynomial in Q adjoined x, and we note that this alpha is a root of f. Now we can't just say that the degree of Q adjoined alpha over Q, we can't say that that's equal to 3 yet, because we haven't shown that f is irreducible. So, let's just assume that f is reducible for now. If it's reducible, we can reduce this into into smaller polynomials, either one of degree 2 and one of degree 1, or we just have, or we can factor this into a factor of degree, into a polynomial degree 1, polynomial degree 1, and another polynomial of degree 1. In either case, we f would need to have some sort of linear factor with rational coefficients. F would need to have a rational root. And therefore, by the rational root theorem, the possible roots f would need to have is are the factors of 1 divided by the factors of 8. So the possible roots are either plus or minus 1, plus or minus a half, plus or minus a fourth, or plus or minus an eighth. We can just check all of the possibilities, and well, we find that none of them are actually roots. Therefore, f is irreducible in Q adjoined x. So since alpha is a root of f, that means that the degree of Q adjoined alpha over Q, that's going to be equal to 3. But since alpha is also constructible, that means that the degree of Q adjoined alpha over Q must be a power of 2. So that means 3 is equal to some power of 2, and that just isn't true. If we try and solve it, that means that if 3 is equal to 2 to the power of r for some non-negative integer r, that means that r is equal to the log of 3 base 2. We have a contradiction. Therefore, data is not constructible, and you cannot trisect a general constructible angle. There you go.
Is doubling the cube, and this was proved to be impossible using just simple compass and straight edge constructions. So this problem is also known as the Delian Problem. So the story behind this problem is that in 430 BC, a great plague struck Athens, and the Athenians consulted the oracle at Delos to find a way to stop this plague. And the oracle said that the plague occurred because Apollo was angry, and the only way to stop it was to double the volume of Apollo's altar, which had the form of a cube. And he said this because just of the attitude around geometry, and he knew that they wouldn't be able to do it. And so the Athenians tried to double the length, height, and breadth of the altar, but obviously the volume wasn't doubled, but it was 8 times larger because they doubled the sides, and this made Apollo even angrier, and the plague persisted until about 423 BC. So obviously this is a legend and could be true, but also just shows the idea around the problem and its impossibility. So in 1837, French mathematician Pierre Lorentz proved doubling the cube is impossible. So he actually began by considering a system of quadratic equations, and he basically said, okay, let r be like the root of our irreducible polynomial f of x, and that if r is, if the degree of f is not equal to 2n, then r is not constructible. So following that, we basically want to show that doubling the cube is impossible, and we'll show that using our theorem. And so say we have some cube. We want to, doubling the cube means we want to show that it's impossible to construct a cube with twice the volume of our original cube. So we know that the volume of a cube is V equals A cubed, where A is one of our sides. And so let's focus on the construction of the sides of our cube. So let's say that this one is like our original side of our cube, and this one is the theoretic doubling the size of our larger cube. So we're going to say that's A and that's B. So let A be the side of our smaller original cube. And then let B be the side of our larger cube. Okay. So our goal, let's state our goal, is to double the volume. So we want 2 times V, 2 times the volume. So this means we want B cubed, because that's our side of the larger cube, to be equal to 2 times the volume. So we know for our original cube, the volume was A cubed. And so we want 2 times A cubed to be equal to B cubed. So B, by taking the cube root of both sides, is going to be cube root 2A. So ultimately, the problem then boils down to if the cube root of 2 is constructible. So really, it's like the point 2, 1 cubed 0. Or, sorry, 2 to the 1/3 0. So we want to consider x cubed minus 2 equals 0. And we know that the cube root of 2 is a root of this equation. So we want to use our theorem that states whether or not a point is constructible. So let's just go ahead and write it out. So we have theorem 6.1. And this states that if P equals XY is a constructible point, the extension Q adjoin XY over Q is finite, and the degree of Q adjoin XY over Q equals 2R for some R in the positive integers. Okay, so therefore, by theorem 6.1, it suffices to show that the degree of the cube root of 2 over Q is not a power of 2. Okay, so first of all, let's consider, can we factor x cubed minus 2 equals 0 over the rationals? So basically, is it irreducible? So we have f of x equals x cubed minus 2 over q of x. And we have that for alpha equals cube root of 2. F of alpha equals 0, so alpha is algebraic over q. And we know from theorem 1.5 that q adjoint alpha over q equals the degree of the minimal polynomial of alpha. So if x cubed minus 2 factors, then one factor must be linear, yielding a rational root. And so we're basically doing the degree 3 2 test. So by the rational root theorem, the only possible rational roots of x cubed minus 2 are x equals plus or minus 1 and plus or minus 2. And we see, I'm going to move this down. That's for later. That none of these satisfy x cubed minus 2 equals 0 because you plug in -1, get -3, 1 is -1, -2 is -10, and 2 is 6. So, thus, x cubed minus 2 is irreducible over q and is the minimal polynomial of the cube root of 2. So, as the degree of the minimal polynomial is 3, we have that the degree of root 2 over q is 3. Okay, so therefore, any extension field F containing the cube root of 2 must have the degree of the extension over Q equal to 3n for some n. And we know that 3 is not a power of 2. So that doesn't follow our theorem because we need it to be a power of 2. So we have that the point, is not constructible. Okay, so essentially we're saying that with a compass and a ruler, we basically can't draw, like if we had the pointy part of a compass and we have the pencil on the other side, the pointy part, say this is our little compass, we can't get the pencil and just basically mark the point. You can't do that with simple constructions. However, there's another type of construction using a marked ruler, and using that way you actually are able to construct the point, but that's basically you're able to mark it, and this is just on it's called a Neusis construction, and so that way you're able to do it. But using our simple construction with a compass and ruler, we're unable to do that. So that's it for that proof. And I just wanted to bring up a little bit about like polygons being constructible. So essentially, Gauss included that for a regular polygon to be constructible, it had to have the number of sides whose odd factors were only distinct Fermat primes. So let me go ahead and talk about those. So let's do a quick polygon constructibility. So basically the primes that Gauss was referring to, the Fermat primes, so those are going to be the form 2 to the 2n plus 1, where n's an integer. So they're called Fermat primes because they were discovered by the French mathematician Pierre de Fermat. And he claimed that all numbers of this form must be prime. And then there's only 5 known Fermat primes. So it's really just p equals 3, p equals 5, where that's the Fermat prime. P equals 17. P equals 257, and then P equals 65,000. Imagine drawing that polygon, 537. So we have that those are the constructible polygons, basically, that you're able to do with a compass and a ruler. A straight edge. And so they were wondering at the time, like, is it possible to construct all regular polygons with a compass and straight edge? And if not, like, which ones are it? And so Gauss proved the constructibility of the regular 17-gon in like 1796. And then Wansel was the one that gave that definitive proof of it later on. And so that what Wansel proved basically is that a regular, basically what I've been talking about, a regular n-gon can be constructed with a compass and straight edge if and only if n is the product of a power of 2 and any number of distinct Fermat primes. Okay, so let me see. So we have, like for example, we have that the 256 gon is constructible since it has no odd factors. 257 gon is constructible since it's a Fermat prime. But for example, like the 258 gon is not constructible. Whoops. since its prime factorization is 2 times 3 times 43. So it has primes that aren't Fermat primes. Okay, sounds good.
Hi, I'm going to talk about the impossibility of squaring the circle. So, to begin to understand this proof, we will need the fact that pi is transcendental. So, the proof that pi is transcendental was first done by Linderman in 1882. The theorem used in this proof is called the Linderman-Weierstrass theorem. Or as the Hermite-Linderman theorem. And this is because Hermite proved the simple case of the theorem, but then Weierstrass proved the more general case later. But I'm going to abbreviate this. As the LW theorem for Linderman-Weierstrass. So now I'm going to state the theorem. If alpha 1 through alpha n are algebraic numbers, that are linearly independent over the rational numbers, then e to the alpha 1 through e to the alpha n are algebraically independent over the rationals. So now we're going to talk about the importance of this theorem. So this theorem is quite complicated to use, and I'm definitely not going to prove it. That would take so long. Oops. But the importance for our result is if alpha is a non-zero algebraic number, then e to the alpha is transcendental. So this here is what's really important from that proof, or from the theorem. And using this fact, we will now be able to show that pi is transcendental. Pi is transcendental. Okay, and here's the proof. So if we assume, for the purpose of contradiction, that pi is algebraic, so if pi is algebraic, then so is pi times I. So then, by the Linderman-Weierstrass theorem, e to the pi I, which equals -1, is transcendental. Which is a contradiction. Therefore, pi must be transcendental. So, now that we have this fact, we can continue to show that squaring the circle is an impossible construction. Okay, so given a circle, it is not always possible to construct with a straight edge and compass a square having area equal to the area of the given circle. Let's begin our proof. Let the given circle have radius r equals 1. Then its area is pi r squared, which is just pi times 1 squared, which is pi. For a square to have this area, it would need to have side lengths the square root of pi. For the square root of pi to be constructible, we know from Theorem 6.1 in our Garling book that its field extension must have degree 2 to the r for some r in the naturals. But Theorem 1.5 tells us that since pi, and by extension, square root of pi, are transcendental, then the degree of the extension of q adjoin the square root of pi over q is infinite. And thus, pi and the square root of pi are not constructible. Therefore, it is impossible to construct a square of side length, the square root of pi, and thus we cannot construct a square of area pi, ending our proof. That's not a square. There we go. All right. This is a fun little impossibility theorem that we got to prove. Thanks y'all for listening. Bye.